Hey everyone, today we're looking at two-dimensional motion. Basically we're going to do what we call the riverboat problem, which is an example of two-dimensional motion, but without any acceleration. It's such a specific instance that really there's only like one problem that's like we can really think of that has this, and it applies to crossing a river. There are examples that are more complicated, but for basically the amount of physics we've covered, this is the only example we can really work with. So I keep calling it the riverboat problem. There are other applications to it, just none that we've covered yet. So they all kind of look the same. Let's go. All right, this is an example of two-dimensional motion. It's an object that travels both across and kind of up and down. But for us now, it's going to be like it travels in the east-west plane and in the north-south plane. So let's see if we can think our way through this. And we're going to start with simple one-dimensional motion here. We're going to take a swimmer moving at 0.5 meters per second east. So this is our swimmer. I'm going to represent him as a dot. He's moving at 0.5 meters per second across a 200 meter wide river. So 200 meters wide, I already wrote that in for you. Let's start out with like the simplest physics equation I could possibly give you. For each second that passes, how far east does the swimmer travel? All right, 0.5 meters per second means for each second that goes by, we're going to move east by 0.5 meters. 0.5 meters per second. So after 1 second, we've moved 0.5, 2 seconds, we've moved 1, and then 1.5, and then 2, and so on and so forth until we reach the far side of the river. How long does it take to get across the river? This is as simple as anything I could ask you. We're solving for time. We know the velocity is 0.5. We know that the distance is 200 meters. Keep this as simple as we can. I think it's V equals d over t. 0.5 equals 200 over t. Cross multiply carefully. I think you get a time of 400 seconds. Nice. All right, so this is very simple, right? We've got a person moving in a straight line for a certain amount of distance. That's it. So let's add the new part here. Now, as the person travels east across the river's current is going to push them south at 2 meters per second. Okay, so we're moving east, which again is... Oh, no. Come on. We're moving east, which is... sorry about that. Across the river, right, this way. And now the current's going to push him south at the same time. So, again, this is our swimmer here. While the person moves east, he's also going to get pushed south at 2 meters per second. So I'm just going to move that 0.5 to somewhere else, like over here. Okay, so now let's think about this and what how that would affect our swimmer. For each second that passes, how far across the river does the swimmer travel? So when I say across, I mean just across. So we're not going to talk about how far south they go, how far across. Let's think about that. Does that 2 meters per second push the swimmer across faster? I don't think so, right? Because it's not pushing to the right or to the east. Does the 2 meters per second push them backwards at all? I don't think so. I don't think that's true either. It just pushes them south. So how far across does the swimmer travel for each second that goes by? I think just the same answer, 0.5 meters. 0.5 meters. That's it. That's how far across we move per second. That too had no effect on our eastward motion. All right, did the current affect the swimmer's motion across the river? Again, the point I'm trying to make here is no it doesn't. We still have that 0.5 meters per second across. So if it has no effect on the swimmer's motion across, then how long did it take? I'm just going to go with that 400 seconds again. Again, that eastward motion had no effect on the southward motion. I'm hoping this kind of sounds a little familiar from when we talked about projectiles, how the horizontal X motion had no effect on the vertical Y motion. They were separate. Kind of the same idea here. But let's talk about the downstream motion, because as the swimmer moves across, they're also getting pushed downstream. So we got to figure out kind of what's going on there. For each second that passes, how far downstream does the swimmer travel? Okay, well, we're moving downstream at 2 meters per second. So for each second that goes by, we move 2 meters per second. So as the person travels across 0.5 meters, the person also travels south at 2 meters per second. So how far downstream do we go? Let's think about this. When I say that, I mean, instead of our swimmer landing over here, if there was no river current, that river current's going to push him south a little bit. So he's going to end up somewhere over here. I want to know this distance. Okay, so I want to know how far south they end up. Again, I want this southward distance. So let's think about this. We know the time that the swimmer spent in the river. We know the time is 400 seconds. I know that I'm solving for d, but we got to think about our velocity a little bit because we have a couple of different velocities now. We've got this 0.5 meters per second, this 2 meters per second. Which of those do you think we could use to solve for how far south the person ends up? I'm going to use the 2 meters per second. Because, again, if I want to know how far south you end up, am I really super interested in how far east you go? No, not really. It's a separate motion in a different dimension. So, v equals d over t. Again, we're using the 2 meters per second. Equals d, which is what we're solving for 400 seconds. Multiply across, and you get a distance of 800 meters downstream. Long way downstream. That's like a half a mile. This person probably would have drowned by then. Good. So, no, not that that's good. So we go downstream by 800 meters. Again, the important point that I want to bring up here is, see how to find that downstream distance? We use the downstream velocity. And then earlier, when we solved for the across the stream, we used the across the stream velocity with the across the stream distance. We kept all of our directions consistent with one another. And so lastly, during this trip across the river, calculate the magnitude of the velocity relative to the shore as a result of the combined motion across and down the river. What I mean by that is, this swimmer, they get pushed across and they get pushed downstream. How could we find the total velocity? Well, this looks like a vector triangle, a right triangle, and we've done vector triangles before at the beginning of the year. So, again, we've got 0.5. Oh, this is, oh god, atrocious. And we've got 2. So to find this, that's just the hypotenuse of a right triangle. I think this equation will work for us. 2 squared plus 0.5 squared equals c squared. And you should get an answer that is fairly close to 2, I think. I got 2.06 meters per second. And that's it. That's how you kind of work these. The thing I want to point out is, again, these two motions were completely separate. This was a very basic physics motion. Object moving straight at constant velocity. And then all I did was I didn't change anything. I just added something to it. So while it moves across, it also moves north and south. And when we do the math, we separate our directions. Just like when we do X and Y, we're just calling them east and then, south, but it's the same idea. All right, now you're going to work through a few different quest slides that basically take this whole process and break it down for you again, like sort of very slowly. It's going to follow along with this question right here. The questions mostly, it takes these parts A, B, and C and then drags them out into a bunch of smaller questions. So I know it doesn't fit like perfectly, but you guys are smart kids. I think you'll figure it out. You're going to watch the video, answer all the slides, and then that's it. As long as and then there's one question at the end that it has you work through. So we're just going to take that math part, in case I did that a little quickly for you, and we're going to really break it down for you.